Hello and welcome. I am Alex, the Industrial Engineer. Today's video is the third and final part in a mini-series on operations scheduling. Today's video topic revolves around greater than two resources scheduling type problems and is the logical next step up from the two resources scheduling shown in part 2 of this series. If you have not seen part 1 or part 2, I recommend starting there to really grasp the basics of operations scheduling problems and would really help you better understand today's video. The plan is to cover both the CDS and genetic algorithms in a clear manner. We will explore the differences between each, including understanding their technical details, knowing how to apply them, and overall the use cases of each of them. So let's start with the CDS algorithm, as it is easiest to understand and apply. So the CDS, or the Campbell, Dudek, and Smith algorithm, utilizes Johnson's rule, which we saw this in the previous video. It is notably a heuristic approach, which means it does not guarantee an optimal solution like the brute force approach seen in the first video. However, it is much, much faster at arriving at a generally good solution. Heuristic also means that this algorithm was specifically made to solve sequential scheduling problem known as a flow shop problem, where each scheduled job flows from machine 1 to machine 2, and etc. This was also seen in the previous video, and I'll demonstrate how this works again here. Let's say our sequence is job B, and then job D, and then etc. So job B would start on machine 1, and then once that is done, it goes to machine 2, and then job D starts on machine 1. And then once job B is done on machine 2, job D can then start on machine 2. Just think about a assembly line here. Now that we understand some background information and when the algorithm should be applied, let's understand how to do the CDS. So in technical terms, we need to select M-1 two machine problems from the original M machine problem. And stay with me here. All this means is that we need to perform the CDS algorithm M-1 times, or in our case, 4-1 times. So we need to do the same algorithm 3 times in order to effectively find a low make span, or the best one that the algorithm can provide us. Remember, this is based on Johnson's rule, so we need to somehow turn our 4-machine problem down into a 2-machine problem. Now let's continue to see this in action. So for our first iteration of 3 of the CDS algorithm, I'm going to simply sum up the machine 1 and machine 2 values, and also the machine 3 and machine 4 values. And this is what it looks like after we sum those columns. As you can see, we effectively turned our 4-machine problem into a 2-machine problem, where Johnson's rule can come in and easily solve for us. And the sequence derived from Johnson's rule is here. It is CADEB. Now I'm going to show quickly how this was concluded. So if we go back a slide, Johnson's rule, the first step is to find the smallest number within the 2 columns, and I see that is number 7 here. And this is job C, and it's also in the first column. So that means job C is going to go first. Now that we're done with job C, we look for the next smallest number. Looks like that is number 9 here. That's job A, and it's also in the first column, so that's going to go second. And the next smallest number looks like that would be 11. It's job B, but this time it's in the second column. So that means that we're going to put B last here. And now and this process continues. So we have 13 here. That means E is going to go last. And then our last job is D. So we're just going to fill that in. And there is our CADEB. And this sequence yields a final make span of 57 minutes. And note, this time for this job sequence is applied to all 4 machines. Also remember, this make span is not guaranteed to be optimal, and that we still need to conduct the CDS algorithm 2 more times before confidently selecting a sequence. And for that, I'm going to bring us over to Excel, where I have created a workbook that automatically conducts the CDS algorithm for us. And here we are in Excel. In the upper left-hand corner here, I'll highlight it for you. We have the same given jobs and machine time data that we saw on the slide previously. Now, I incorporated the logic of Johnson's rule into the spreadsheet foreground, as we can see here and here. This all creates the Johnson's rule sequence right here. I automated the CDS algorithm with VBA code in the background. As you can see, this is where we insert our 2 machine times, the 2 columns. And I'll show this functionality step by step later. Recall that we need to perform the CDS algorithm m-1 times, or 3 times total, each with its own unique derivation of the 2 machine times. So I decided to conduct 5 iterations total to really evaluate the results, but 3 is what is called for. So I came up with 5 unique ways to sum up the columns to run the CDS algorithm. I'm going to go ahead and run it, and we can look at the results. Just like that, it is completed. So let's go over to the table. So iteration 1 here, this is that same CADEB that we just saw on the slideshow. And we got the same make span of 57. Remember, we combined the times of machines 1 and 2 and 3 and 4 together to get this result. And the following iterations combine the machines in other unique ways. So iteration 2, I summed up the first through the third column, and then the second through the fourth column to get our 2 columns. The third iteration summed up the first and fourth, and the second and third. And the fourth iteration, the first and third, and second and fourth. And then lastly, I summed up the first, third, and fourth for the first column, and the first, second, and fourth. And let's look at iteration 5 for explaining how the logic works on the spreadsheet, because this is what the code plugged in last. So again, the first column here is summing up the first, third, and fourth column from the original data set. So let's quickly check that it did it correctly. The first, third, and fourth, that would be 16. And we see that number right here, 16. And then this one should be 21 right here. This one is 25, and etc. So we know this is working. And now let's see the Johnson's rule logic in action. So remember, we need to find the smallest number in either column, which Excel finds here in iteration 1 of the Johnson's rule, as I called it. It finds the number 13. It sees that it's in column 2, in row 1, knowing that it's job A. And Excel quickly assigns it to the last part of the sequence because it was found in column 2. And now after we assign job A, I filter the table to remove A so that Excel can look at the table again and find the next smallest number. And it finds that it was 17, and there are 2 17s in the table. But as you'll notice, the other column has a 25 in each of them, so it should not impact our results. And it shows the one in the first column first, that's job E. That means we put job E first. And now we take out job E in the filter and continue the process. And after we have our sequence done, we can calculate the make span which is shown here. Remember, we still have 4 machines, but we had to make it a 2-machine problem to get our sequence. But now we're back to the real world, the 4 machines. So we're going to run the sequence through all 4 machines. So the times in this table are the timestamps in which each job is completed. So as you can see, job E lines up with the first column here, and then it goes to job D, B, C, and then job A finishes on time 65. So it takes 65 minutes to complete all of the jobs in the sequence. So let's look at our results. We have that 65 number right here. And we see that iteration 1 had the lowest make span at 57 minutes. So with the CDS algorithm, we would choose the same sequence we found in the presentation of CADEB. Now we're going to jump back to the slideshow to go through the genetic algorithm now. The genetic algorithm is a meta-heuristic and is inspired by the principles of natural selection and genetics. More specifically, it mimics the process of biological evolution to approximate solutions. Pretty cool, right? And now this slide quickly shows the genetic algorithm in its entirety and all of its functions. So let's take it one step at a time to really understand how it works. So real quick, from the previous video, we know that when we have 5 jobs, we're going to have 120 unique sequences possible. And I'll show how this was derived. So we have 5 slots to assign our letters to, A, B, C, D, and E. So we have 5 letters to pick for the first slot. And after we pick that job, we have 4 remaining. And after we select these first 2, we have 3 remaining, and etc. Now, if we use the product rule from combinatorics, if we multiply all of these numbers together, it's equal to 5 factorial or 120. So there's 120 unique permutations that the final sequence could be. And this 120 is representing our overall population here. So I couldn't fit all 120 on this slide, but think about this overall population having 120 unique sequences. If this were a real-life problem, the brute force approach shown in the first part video of the series would be ideal to find the best sequence, as the genetic algorithm is meant for larger sample spaces. But for the purposes of teaching the algorithm today, we're going to go with it. So we have 120 unique sequences in our overall population. The first step of the genetic algorithm is to create a sample population derived from the overall. So it's just a random batch of letters. So in our example, I only took 4 from the 120. So we have our 4 sequences here. These are possible candidates for the answer. Now the second step is to evaluate each sequence in our sample population. And as you've probably noticed, I have color coordinated this throughout the slide, so it's easy to follow and match the sequence to the performance. As I have stated before, sequences with lower make spans are better. Therefore, our fitness function, in this case of the genetic algorithm, is calculating the make span of each sequence. Now, from these make spans, or the fitness function value, we need to determine which sequences become parents of the next generation. Now, there are a few ways to do this, but the most common way is to assign a probability to each sequence in the sample population based on how good their fitness function score was. And this mimics the process of natural selection, where the top performers, or the ones with the lower make spans, pass their genes onto future generations. And notice how the CADB sequence here was chosen twice to be a parent. This is because it had the lowest make span up here, and so it had a higher probability to be selected as a parent. And this is somewhat a simplified explanation of how this works. There is some math in the background, obviously, but I hope this makes intuitive sense when comparing it to natural selection. We can see that the BADCE sequence here, with the highest make span, ended up not being selected as a parent because it was the worse off. And with the parents now selected, we create 2 offspring from each set of parents so that the sample population is replenishing itself. And to do this, we set a random cutoff point where the genes are spliced and merged together. And I'm going to go through this real quick. So in our example, the random space is at 0.2. I'm going to draw a line at the second letter in. And comparing the letters over here with the letters in this step, we can see that we took AB from this parent and combined it with DEB from this parent, and that is this sequence here. And the same thing for the second offspring here. We just took the CA right here and combined it with a CDE from here. Those colors are matching up. And the same happens with this second set of parents on the bottom row. However, in this stage, there is a chance for a mutation to occur, which is represented by this red color right here in this offspring. And what a mutation does is it randomly flips 2 genes around in the offspring. This introduces natural variability in the algorithm, so we can effectively search the overall population with more unique sequences. Now that the offspring is created, we now repeat this process. So we go all the way back to the fitness function and calculate that again, make new parents, make new offspring, and you can tweak the parameters of the algorithm. You can say how many generations it runs for, how big the sample population is, how probabilistic the mutation rate is, and etc. And now to show the genetic algorithm in action, I wrote a Python script to solve the same problem we saw before with the CDS algorithm. And here we are in VS Code. Recall that we have jobs A, B, C, D, and E, and those are right here. And we have machines 1, 2, 3, and 4 that we have seen earlier. And here are those parameters I was talking about just recently for the genetic algorithm. For this demonstration, we will run the algorithm 50 times. Here's the number of runs variable, where each run consists of 10 generations. So that cycle that we saw on the slide, we're going to do that 10 times, and our sample population is 10. And we already know there's only 120 unique sequences, so we're just going to draw 10 random samples for each start of the generation. So I'm just going to go and run the program, or I'll quickly scroll through so we can see the code. I won't go too in depth of explaining it. Each block of function here is one of those steps that we saw on the slide. So I just clicked run and it's done. We're going to come back to this graph in a little bit. We're going to check out the terminal. remember, we ran the algorithm 50 times, and for 10 generations, starting with a sample of 10. And what the program outputs to me is the best overall sequence seen throughout that entire process, along with the make span. And to better look at this data, that's where the graph comes in. As we can see, we have 50 runs on the x-axis, and we have make span on the y-axis. And we can see the genetic algorithm going up and down. And this is where that natural variability of the genetic algorithm comes from. It tends to go towards the lower make spans from the natural selection, but there is a chance where other make spans are possible. But as we can see, across all 50 runs, the algorithm was not able to go under 57 for the make span. And we can confidently say, knowing what we know about the overall population, that we have found the best sequence possible. We can't go lower than 57 for the make span. This is also what the CDS algorithm told us earlier. And now that we have seen both algorithms in action, I wanted to end the video comparing and contrasting each. Let's start with the CDS algorithm. It is a heuristic approach, meaning it was specifically built to solve operation scheduling type problems where we have greater than 2 machines or resources and any number of jobs. The CDS algorithm is also easier to learn, set up, and perform, and also analyze. Now, the genetic algorithm, on the other hand, is a meta-heuristic, meaning that it could be applied to a plethora of problems. We would simply have to change the meaning of the sequence and what the genes are. I've applied this genetic algorithm where my DNA sequence was binary, just ones and zeros. So just the way you structure your problem, you can apply the genetic algorithm. However, it is a harder algorithm to learn and set up properly. As you saw, the Python code does go pretty in depth. While the algorithms do have their differences, they were both able to find the same result, with the make span of 57 being the best answer. Also, both algorithms are scalable to this type of problem. It can handle any size matrix of any number of machines, any number of jobs, as big as you want. And that is the conclusion of today's video. I thank you for watching. If you learned something new today, please leave a like below. I would greatly appreciate it. Until next time.